All right, in this video, we are going to start talking about geometry, specifically with constructions in the next few videos. So you will need the lesson 1 packet that's attached to this Google Classroom. That's actually, no, you will need a compass, but I don't think you need a ruler today for this video. Okay. So on lesson 1, opening exercise, I kind of tweaked this a little bit because the problem on the actual packet I thought was kind of boring. So, and I like Ghostbusters. So we have Egon and Ray who are in a park trying to catch a ghost. Venkman joins them, and they have to stand so that the distance between any two of them is the same. This is so that they don't cross the streams from the Ghostbuster ghost catcher things. It's kind of hard to explain if you haven't seen Ghostbusters. If you haven't seen it, you should go see it. But if you have seen it, you'll know what I mean. Don't cross the streams. Anyway, so we want to position these three guys, Egon, Ray, and Venkman, so that they are basically the same distance apart. So obviously this isn't going to be the same distance apart, but I'm just kind of giving you a visual here. So we want the length between each of these three people to be equal, right? So we want those three lengths to be equal. So the question is, how do we do that? So I want you to see if you can brainstorm some ideas on how they could do this in a park setting. Okay, some of the ways that classmates came up with were, and you can write these down for the opening exercise, counting footsteps. So have one of them stand in position, and then one of them will count how many footsteps to get to the second one. Then they'll count how many, mark a spot, count how many, mark a spot, and make sure that they're all equal. So you could count footsteps. Somebody else said use a rope or measuring tapes. So a lot of things you could actually do. The problem is being very precise with this. So let's try a similar problem, but emphasize precision a little bit more. So on problem number 1, exercise number 1, example 1, we have Margie who has 3 cats. She's heard that cats in a room position themselves at equal distances from one another and wants to test this theory with her cats. She notices that Simon, her tabby cat, is at the center of her bed at S. So here's Simon. While Jojo, her Siamese, is lying on her desk chair at point J. If the theory is true, where will she find Mac, her calico cat? So we want to basically use this drawing to demonstrate where the third cat would be. Okay, and again, we want the distance between all these cats, wherever the third one is, to be the exact same. And we want it to be very, very precise. So you can use, and you can only use, a compass and a straight edge, meaning a ruler. Okay, compass and a straight edge. See if you can figure it out. I want you to pause the video, try it out for a couple minutes, see if you can come up with anything, and then come back. Okay, assuming you tried to figure this out using a compass and ruler or both, let's see what we can actually do. So a lot of people will try using a ruler to measure the space between J and S, right? And then kind of arbitrarily pick a spot up here because we know that's going to be the general area, and measure and measure. The problem with that is preciseness, exactness, right? when we pick a spot randomly, we don't know if our angle is perfect, right? So it's gonna be very difficult with just a ruler involved. However, with a compass, we can get a little more tricky. So what I want you to do, and it's kind of hard to demonstrate this without actually being able to show you my hands and stuff holding a compass, but grab your compass, put the point of your compass on point J, and then the pencil end of your compass spread out to have it rest on point S. So pointy part over here and the pencil part over here. Okay, then what you're going to do, keeping the pointy end on point J, you're going to rotate the pencil part, and it's going to end up drawing an arc, kind of like that. Okay. And then you're going to do the same thing, but this time you're going to start with the pointy part. Oh, that's way too big. You're going to start with the pointy part on this side and the pencil part over here. And the distance or the length between the two shouldn't change. So you shouldn't be adjusting the compass at all when you switch where the pointy part is. Then you do the same thing. So draw an arc using the pencil part. Okay. And then wherever those two intersect, let's do rainbow. Wherever those two arcs intersect, go, you can do it. Just make it really thick. There we go. Wherever those 2 points intersect is going to be an equidistant point between the first point and the second point, which would also be the same distance between these 2 points. Okay, because we used that arc, that radius or circumference, to draw that distance, the distance between them would be equal. Okay, and that would give us an equilateral triangle, which gives us equal distances between each of our 3 points. Okay, again, it's kind of hard to explain without being able to show you how to use the compass, but hopefully that made sense. And I would definitely watch the videos I've attached to the lesson that are like the GIFs of it, of how to use the compass, or the YouTube video link on there. Okay, so there's example 1. Now I want to talk about this guy named Euclid for a minute. This guy named Euclid. He was this Greek mathematician, Euclid of Alexandria. He is known as the founder of geometry, and he lived around 300 BC. Now, what's cool is the reason he's known as the founder of geometry is because he's the one that actually came up with proofs and definitions, like precise definitions and proofs of a lot of the geometry knowledge we have today. And a lot of that had to do with construction, so how to form specific shapes. This book was called The Elements, and it's actually the second most printed book in the world, second to the Bible, which is pretty cool if you think about it. So basically in this book, he wanted to be able to prove these geometric theories that people had, which started as assumptions, were deduced to theorems, and then he proved them to back up these theorems. So he proved and demonstrated and defined precisely different geometric things, which is pretty sweet, which is why, again, he's known as the father of geometry. There's a couple assumptions that are key. For example, there are points on a plane, right? If we ever have a plane, like a space, think of a graph, a plane, coordinate plane. there are points on a plane. There's exactly one line that contains the points. So, for example, if we had, let me actually drag this over here a little bit so I can demonstrate what he's talking about. So let's say we have this plane over here, this space. If we had a bunch of points on that plane, there's going to be exactly one line that would contain all of those points. One line. There is no other line besides that one that would contain all of those points. We can also name the distance between the points, right? We can calculate the distance. And we also know that every line has a coordinate system, hence we could be able to calculate the distance. Right? We can't calculate the distance between something if we don't know where the scale is or what the scale is. Okay? Which, again, all these seem pretty obvious, but again, he was the first one that did actually define these things and prove these things that do, again, seem very obvious to us today based on what knowledge we have now, but yeah. So let's talk about how to construct an equilateral triangle, which he does define in his Elements book in detail, but I kind of broke it down for you a little bit more in a shorter amount of words. So on your lesson 1 packet, under the, let's see, where do I want you to write? Under the sitting cats example, I would write down these steps. So I would just write something like steps for equilateral triangle. And then I would write these steps down, and I'll demonstrate to you what these steps actually mean. So after you write those steps down, come back and I will demonstrate what these mean. All right, so the first step would be to draw circle A with center point A and radius AB. So we're actually going to have a line with radius AB. So a line with 2 points on it, 2 end points. Nope, that's not what I meant to do. Okay. So let's say here, this endpoint is point A, this endpoint is point B. So we have radius AB, and we're going to draw a circle around point A. That means the center of the circle is A and our radius is AB. So the distance around point A needs to be the exact same. Now, obviously, I can't make it exact because I'm a human and I can't draw perfect circles without a compass, and I can't really show you how to use a compass on here, so just pretend that's a perfect circle. So there's our circle A with center point A and radius AB. Now we're going to draw circle B, which has center point B and radius AB. So the same radius, we're not changing that at all. So when you draw this with a compass, I should back up a little. Put your pointy end of the compass on point A, stretch out your pencil end to point B, and then draw an arc with your compass for the circle A. Then you're going to do the same for B. So put the pointy end on B, put the pencil end on A, and it shouldn't have changed the distance at all because we're using the same radius. And then from there, you're going to draw an arc around center point B. Something like that. Okay. And then on the intersections where those two circles intersect, you can pick either one you want. So you could do this bottom one or this top one. And then you connect them with a line. So we already have AB for our triangle. And let's maybe name this point C. Point C. Okay. Point C. There we go. We're going to draw a line from C to B and C to A. And there we have our perfect, not so perfect, because again, I'm drawing this by hand. You should be using a compass though, and it should be perfect. Our perfect equilateral triangle. So all those sides should be the same length. And again, you could use either intersection, so you could have your triangle going this way instead of up, and that's totally fine. Either way will give you a perfect equilateral triangle, meaning all sides are exactly the same length. Okay? And I do want you to practice this using your compass. Don't just draw it by hand like I did. Because we're working on preciseness with this specific module, I do want you to be as precise as possible, which means you need to use the compass. Okay. Okay, let's go to another problem. Nope, we don't need to do that. Here we go. So we're going to do the problem set. I'm going to walk through number 2 with you. We actually just did number 1. Number 1 on the problem set for lesson 1 was to write clear steps for construction of an equilateral triangle, which we just did, right? I had you write this down. So you don't need to rewrite it if you already wrote it. But you would draw circle A with center A, radius AB, draw circle B, center point B, radius AB, label one intersection of those circles as point C, and connect the points. So that's number 1, clear steps to construct an equilateral triangle. And by construct, we just mean draw, okay? But let's look at number 2. Number 2. Suppose 2 circles are constructed using the following directions. Draw circle, center A, radius AB, and draw circle, center C, radius CD. Now you don't have to draw anything yet, but to answer the questions A, B, C, and D, you can either write a sentence or draw a picture. And I'm going to actually walk through these with you if I can find where it went. There it is. Okay, so question A. Under what conditions would the 2 circles have only one point in common? So think about having 2 circles that only intersect at exactly one point. What would that look like? Maybe draw a picture if you can think of what it would look like. So what you should have drawn is something that's going to look like this. And again, I'm drawing this by hand. You should be using a compass. But it should be the 2 circles and they touch at exactly one point. Okay, so that would be A, touch at exactly one point. So what would no points in common look like? Well, that would look like 2 circles that are just spread apart, right? They're not overlapping at all. Problem C then, 2 points in common. Well, we kind of demonstrated this on the few examples we did, like the sitting cats example and the Ghostbusters in the park example. 2 points in common would look like this 2 circles overlapping or intersecting twice. So they're not overlapping on exactly one spot. They're overlapping in 2 spots now. They have 2 points in common. So then what would, on D, question D, what would more than 2 points look like? Think about it. Well, it would be the exact same circle on top of each other. And obviously that's not a great demonstration because I am doing this by hand, but imagine 2 circles that are exactly the same, have exactly the same circumference, and they're piled on top of each other basically. So instead of overlapping twice, like here, they're overlapping on every single point. Okay. Okay, for number 3, I'm actually going to let you do number 3 by yourselves. So essentially be doing the same thing as the sitting cats and the park example. So go ahead and do that. And again, it's kind of hard for me to demonstrate how to do it by hand on here. So I would reference the other YouTube video or the GIF that I attached to this Google Classroom lesson, because they actually show the compass and how to use it. So if you need that, reference that and then do number 3. Okay, and you'll be turning in that problem set. You could turn in the whole lesson since it's all stapled together, or just turn in the problem set page. Either way is fine. Just make sure your name's on it. And that's actually it for this really short introduction on geometry constructions. Moral of the story, Euclid was awesome, and he had so much knowledge to give us, and it's crazy that the Library of Alexandria was burned down and all that knowledge kind of disappeared, but luckily the Elements book was saved, and we know about geometry proofs and constructions. And now you know how to construct an equilateral triangle. All right, let me know if you have any questions.